Movies make elevator failure look simple. One cable snaps and the box drops, but in a modern traction elevator, that cable is only the first layer. Cut the electrical power, and the expected disaster begins with the opposite action. A spring-loaded brake closes. Losing power tells the machine to stop. That is the first answer. Elevator safety does not depend on one heroic cable. It uses layers that react differently as the danger escalates. Start at the top. A traction sheave, suspension ropes or belts, the car on one side, and a counterweight on the other. The motor turns the sheave, and friction moves the whole system. The counterweight balances much of the load, reducing the work required from the motor. There is no single universal rope layout. Different installations use multiple steel ropes or coated steel belts according to their design and safety requirements. During a normal stop, the drive slows the car and the machine brake holds it. Springs press brake surfaces together. Electrical force releases them. So, when electricity disappears, the release force disappears too. The springs still work and the brake applies automatically at the machine. But that brake is not the entire answer. What if the car moves too fast anyway? A separate mechanical device watches its speed. It is called the Overspeed Governor. A wheel connected to the elevator car by a governor rope that moves whenever the car moves. If the car exceeds a preset speed, moving weights inside the governor swing outward and trip a mechanism. The exact threshold depends on the installation. The governor grips its rope. The car moves a little farther, but the now stationary rope pulls a mechanical linkage mounted on the car. That linkage activates the safety gear, wedges, or clamping jaws press against the guide rails running along the sides of the shaft. Those rails normally keep the car aligned in an emergency. They become braking surfaces. The guide becomes the thing that stops the fall. The sequence is entirely mechanical. Speed moves weights. Weights trip the governor. The rope pulls a lever, and the lever drives the safety gear. That independent chain is designed to stop dangerous downward overspeed, including scenarios in which a traction elevator loses its normal suspension support. This does not mean every elevator is identical. Hydraulic elevators work differently, and exact equipment varies. We are tracing a common modern traction system. Even the suspension is layered. Multiple ropes or belts share the load, unlike the single dramatic strand that movies like to cut. But redundancy is not magic. Each layer has a job. Suspension carries. The machine brake holds. The governor detects speed, and the safeties grip rails. Sensors and controllers add another layer. They monitor speed, position, and door locks, and a broken safety circuit prevents normal operation. Electrical monitoring is the first line, not the final catch. The mechanical backup still matters because the failure itself may include lost electrical power. There is one more visible layer at the bottom of the shaft. Buffers. They are not giant springs meant to bounce a falling car upward. Their design depends on the elevator, but their purpose is consistent. Absorb or dissipate remaining energy if the car travels beyond its normal limit. Buffers are the final boundary, not a substitute for the governor and safety gear. Catching an elevator is a sequence, not one heroic device. And a sequence only protects people when its parts are maintained. Brakes, governors, safeties, buffers, doors, and control circuits all require inspection and testing. That is why elevator safety codes cover more than construction. They also address operation, inspection, testing, maintenance, alteration, and repair. If an elevator stops during an outage, use the alarm or emergency communication and wait for trained help. Do not force the doors open yourself. Now, replay the chain. Power loss applies the brake. Overspeed trips the governor. The governor rope activates safeties. Overtravel reaches the buffers. No single layer has to carry the entire story. The point of redundancy is to keep one fault from immediately becoming a fall. The cable is the most dramatic object in the shaft. The more important idea is the logic around it. Fail safe, then fail safer. On the surface, an elevator is a panel of buttons. Below that interface is a mechanical chain already waiting for the moment something goes wrong. So, a stopped elevator can still be serious and inconvenient. But stopped is exactly the safer state this hidden system was designed to create.